Again, good morning. I'm Bhupesh Adhikary. I work as air quality specialist at ICIMOD. And the topic I'm discussing today is really theoretical. It involves a lot of physics, chemistry, math, but I've tried to keep it simple. And I'm just going to give you a brief introduction and a lot of the application so that you can actually use how people use models, or when you report stories that are from models, what are the uncertainties, or what exactly did they do? So I just give you a glimpse of it. How do we study air pollution? Okay, there are several aspects. One is in situ measurements. It could be ground-based or airborne-based. Here is a picture of airplanes when you're looking at how things fly to Antarctic, or how pollution flies over Himalayas and it's causing glacier melting and all. You actually have airplanes where, in your windows, there's probes where you can sample air that's coming in, and you measure on real time while you're flying. Okay, so in situ there. Satellite, which is looking upwards, such as this sun photometer, and then top down from using satellites looking down on the Earth. Okay, both of these measure column amounts, and you'll hear the next lecture will talk more about satellite. And then the other way of studying air pollution is using computer models. Okay, and this is what we mean by high-powered computers. Here's a rack of computers. Each little line there is one computer. So you can imagine this around several hundred computers all tied in, and then working together in parallel to do a computing job. Here's what we have at ICIMOD. So this would be like that big. It's around 160 cores. So I'll show you some examples, which was done using this computer. So basically, it's 160 computers working together at the same time. Okay. Again, 3 different platforms to study air pollution. Okay, so air quality models. Okay, what are they? Also known as air pollution model or chemical transport model. Okay, which are different from general circulation model, which is more towards climate or weather related. Okay, and we're talking more about air quality, air pollution models here. So when you talk about model, what is it? Basically, it's a replica. It's not the real thing. It's trying to simulate the real thing. Okay, so they're trying to simulate behavior of pollutants as if in the real world. Okay, so how complex or how good is the model? Okay, if you're in terms of air pollution, how complex is your physics, how things move, your winds, chemistry, what are all the reactions? What level of details do you put in terms of reaction? Geography, okay, how well do you characterize city, valleys, trees, stuff like that. And then, of course, your metrology and then emissions. How well do you know how much carbon is coming from buses, how much carbon is coming from your brick kilns, your cook stoves, stuff like that. So basically, you can make the model as simple as possible, assuming very simple emissions, simple geography, stuff like that, or make it complicated. And then your computing capacity, why would you need 300 computers running simultaneously, is a function of how complex this model is. Okay? And they're all running at the same time. And then without going too detailed into physics or the math, they can be deterministic, meaning based on first principles, like say gravity or first law of thermodynamics, or statistical. What happened last year, what's going to happen this year? Or what happened yesterday, today. So statistical is a lot different from deterministic. And these are relatively simple models where you don't really need 300 cores. We call them cores, or 300 computers tied together. Okay, so and then there are different types of model, which are defined in terms of time, coordinate dimension, and the scale, which I'll talk about next. But first, why models? Okay, why do we even study about models? What's the advantage? If you can just measure, or you have satellites, why even bother using models? If they're complicated, needs a lot of computers, manpower, all that. Okay? So if you look at in situ measurements, they all have their advantages and disadvantages. Okay, all 3 platforms. So if you look at in situ measurements, suppose you're measuring temperature outside, here, okay? Does that represent all of Kathmandu? Suppose if it's raining here, okay? Does that mean it's raining all over Kathmandu? So it has a representative issue of representation, okay? How representative is that measurement, okay? The other disadvantage that measurements have is it can only do past and present. You can only talk about what's happening now or what happened yesterday when you measured it. Okay? Measurements cannot tell you where things came from. You can only measure CO or CO2, but it cannot tell you whether it came from cook stove or it came from buses, all that. Okay? Let's talk about satellite. Okay, again, the same thing with satellite. It can only talk about past and present, near real time. Okay? And the next topic, you'll hear more about it. Usually, it's a column amount. Satellite doesn't give you near there are clever techniques on how to do near surface measurements, but usually is a column amount. Okay, so from the surface of the Earth all the way to the top of the atmosphere. Okay? There's a lot of uncertainties related to retrieval, how you come up with pollution levels, clouds. Like some satellites don't see pollution when there's cloud, when it's covering, stuff like that. And then the other issue is swath lengths. As you'll hear in the next slide, satellites don't cover the Earth throughout. Like on the whole spatial scale, there are gaps in data. And then some satellites only cover the same location once every 16 days or once every week, that sort of thing. So there are some issues with temporal resolution. So, and of course, both of these have a lot of advantages. They measure accurately. There's a lot of good things about it. I just want to, because I'm talking about models, I'm trying to highlight their limitations, so why we need models. Okay. So first thing models can do is, this should have been the first. They provide a link between emission sources and observation. And you'll see when I show some example what that means. That's the first thing models can do. So you take a puff from a brick factory and then you follow down and then see where it lands. This is something that only models can do. Okay? Satellites or measurements cannot do. Okay? So using that, you can understand the role of, okay, what's the role of meteorology? What's the role of emissions? Stuff like that. For example, ozone. It's not emitted in troposphere. It's formed by reactions with NOx and VOCs. So you need to have a model to understand where it's coming from because there's no ozone emission as such. Right? Another big advantage with models is you can talk about future, what's going to happen tomorrow or like next year, okay, which both of these platforms can't do. And then it's because you can link emission sources with observation is a very important decision support tool. And I'll show you examples of that. Okay? So you can do what if scenarios. What if all the buses were to be turned into CNG? What's the advantage on black carbon concentration? Stuff like that you can only do using models. So without, again, going into the mathematics, there's different types of model. There's two different viewpoints, what's called a Lagrangian and a Eulerian. This is where you follow the puff. So things are emitted in an air parcel, and as the parcel moves, you follow the pollution. Okay? There's advantages and disadvantages of this. Another version is what's called the Eulerian method, where you create a box and things come in and move out of the box. And then there's chemical reactions going on, and you calculate. There's different math to these viewpoints, and they both have their advantages and disadvantages. So this is the viewpoint, and for both of these, you can have a box model, a columnar model, where you go from surface to the top, two-dimensional sometimes. And it's not like these simple models don't tell you information. Okay, sometimes you want, there are cases where a simple box model could tell you a lot of information that you're looking for. For example, if you look at Kathmandu Valley, okay, it's surrounded by hills, and then because of the boundary layer height, things are not going past the boundary layer. So you can just use a box model to see what's going on in your atmosphere. Okay? And then, of course, the three-dimensional model where you look at the surface, both in X, Y, and then also vertical. And I'll be showing you example of 3D model, which is where you need the most high power computers. Okay? And sometimes 2D models are just as good. You know, if you want to look at how far a plume from this stack falls X distance away, yeah, you can use a two-dimensional version of this Gaussian plume rise model and then calculate how far does your plume go and deposit. Another aspect you have to think about is spatial scales. Okay. So now if you look at, so again, now I'm focusing mostly on these type of 3D models. Okay. So if you look at these 3D models, now you have to, the next question is, okay, what's the scale? Okay. So there's global scale, which is basically simulating the whole globe, air pollution. And they are usually run in these box sizes. So this size, XY sizes, would be around 100 to 500 kilometer. Okay. And why? This is because of, again, complexity of the model is proportional to computing capacity. So if you have unlimited capacity, you can run global model at 1 kilometer resolution. So because of limitation in computing, these are usually run, the current day global models from NASA are run at around 1 degree resolution, which is around 100 kilometers scale. Okay? Most climate models that you read in newspapers saying, oh, such and such is going to happen, is run approximately around 100 kilometer scale. What that means is, like, Kathmandu is 20 by 20. So that model grid would have 100 kilometer by 100 kilometer. That includes Kathmandu, Banepa, Dhulikhel, Nagarkot, all in one box, and is saying something about that box within that 100 kilometers. So when you use a global model, so again, so let me get back. So the next one is called a synoptic scale, where you only take a portion of your globe and then try to simulate what's going on within this. And these are usually now are run in 15 to 100 kilometer scale. Okay. Mesoscale is when you're doing cities. You can even go a bit further out than cities. These are 1 to 50 kilometers as computing is increasing, capacity is increasing exponentially. These are going down to 1 kilometer. And then microscale, which is around buildings or really small scale, and these are few meters. The issue is, like, say, okay, what should you as news story writers should understand from here is, okay, if they're talking about something about Nepal or Bhutan using a global model, how much can you really say about it? Okay. The scale, so when you say things, okay, like, say, if you use a global model which is run at 500 kilometers and you say, oh, such and such temperature is going to rise. Okay. Again, Bhutan from Phuntsholing all the way up to the Himalayas, it's all in one box. So they're saying whatever is in Phuntsholing to top of your mountain is just one box and it's same. Okay. There are uncertainties related to that. But that doesn't mean you cannot say things using global models. Again, you have to understand what the situation is, and can global model represent, or do you need a mesoscale model, or do you need a microscale model? What is the question at hand? Okay, so here's a typical mesoscale model, chemical transport model. This is what I worked on in my PhD, and I'm working on here as well. Again, complicated figure, but basically how models are run. And I'll show you graphical output. And then again, there's a lot of math, physics, chemistry involved, and I don't want to get into that. So basically, there's a meteorological model that gives you data on your wind, temperature, RH, all the meteorological parameters needed to drive your pollutant and cause reactions. Okay? There's information about emissions, so large point sources, all your big power plants, all your factories, biomass emissions is your forest fires, biogenic emissions, emissions coming from forests, that sort of thing. Area emissions is what in our language is or diffuse emissions, like residential, cook stove, transport, And then volcanic sources, big ones. They all are fed into emission model, and then that ultimately goes into your chemistry model that calculates your pollution concentration. Of course, we also take in observed satellite data as a starting condition to run your model. And then you look at your output using some graphical software. Okay? So quickly, again, go back to, I start with emissions. I'll show you metrology and then satellite, and then show you the chemistry. So this is what a sample emissions inventory would look like that Prakash talked about on first day, saying this is very necessary. This is a global scale at 10-kilometer resolution. And most of our South Asian member countries don't produce this at a high resolution. There's no local information. These are all done using global statistics, World Bank book, UNEP book, FAO book, global, like national level data. And you come up with, like, this is for black carbon. Okay, what's black carbon emissions total here? Okay? And how much is it coming from industrial sector? Here's the data. How much of it is coming from shipping? How much of it is coming from beacons? There's a lot of these different sources. These are compiled, and then you take this big data that you feed into the model. The next one is meteorology. Okay, here's a sample meteorological model running. This is for temperature, how temperature is going. This is for winds, how winds are going at the lowest layer. Of course, you're going top level as well. This is for precip. Again, these are all animated, run for every time step. This is what goes into your chemistry model. And then, again, you'll hear more about satellite, but we also take some satellite data as an initial starting condition. So what's the total ozone column like? And then there are clever ways to put it on different layers and use this as a starting condition to drive your chemistry model. And again, I don't want to go into it, but this is the equation that most Eulerian models run, try to solve for every grid cell. Okay, so if you have like the MET model that I just ran here at ICIMOD, this is 400 by 400 times 40. So you would be solving this equation 400 times 400 times 40 for every time step. Okay, so if you're running 3 days, 4 days forecast out, or you're running 1 year times that many time steps at resolution of, like, say, 15 minutes. So you're calculating all that. So this is why you need high power. Okay? And then I just gave you an example here. There's 7 reactions. Typical CTMs have 50 species, 100 reactions. The version of the model I am showing you has 93 species, 93 pollutants, and then 225 chemical reactions. And you have to calculate all. And in terms of physics, there's just too many physics options, so I don't want to even go into it. Okay, how do you calculate your radiation? How do you calculate your particle growth? How boundary layer options, all that. Okay, your cloud, parameterization, stuff like that. Now the next thing is, okay, you know what's going into the model, different sources. Okay, how good is your model? Okay, so before you start using models to say something, you have to always validate. Another thing that you need to think about when you report on model-based studies is how are those models validated? Because I can show you pretty pictures, but there's just animations, unless they give you some sense of how good they're doing with observation. Okay, so here I'm showing you a graph of at one station. This is, I'll show you a picture later, a base camp of Everest. We're trying to simulate temperature. So all the blue ones are model, all the red ones are observation. Okay, so there are some skills. Okay, it captures seasonality. This is one for the whole year, run at every 15 minutes. Of course, there's some lower bias. There are some issues. Again, same thing here. There are some skills. It's capturing the pattern, but then there are some issues. Same thing here. So these are comparison with point stations. You can also do comparison with spatial scales. So this is my metrology comparing with trim satellites. So this is what the satellite is showing for rainfall. This is what the model is showing. Of course, there's, again, some similarities on the Western Ghats here, but model is high, predicting high, again, similar. I mean, there's all these issues. So given the strength, how good is the model with compared to observations is what you need to understand before you start reporting on it. Okay? So now, without going into physics, okay, what are applications? Why should we care about? So first thing is it gives you regional distribution. Okay, so I'm showing you here black carbon simulation. Okay. And it's easy to look at animations to try to see how things are moving, where it's coming from. And so here, this is for the lowest layer. But in the model world, since it's a 3D, I can look at, okay, what's CO, black carbon concentration 1 kilometer above, where it starts impacting with your monsoon, as Vanessa talked about yesterday. Okay. How much of black carbon is lifted? How much is at the lower level? Now, stuff like this you can only do using a model. Satellites cannot tell you, or not as good as models or observations. It's very costly to fly airplanes and try to measure black carbon at 1 kilometer every day. Right. Another use of a model is, okay, not just one pollutant. Okay, here's a 3D visualization of the same thing. This is pollution. I was doing a project on pollution transported from Asia to North America. And what I'm showing you here is a 3D version of dust from China and the Middle East. How is that mixing with CO only coming from China? And then the arrows are wind barbs, okay, whether it's above 2.5 kilometers or lower, how are they being mixed? And with white clouds, how are they being deposited and all that. And it helps you visualize this. Interpret observations. If you look at observations, the red again here is observation. Okay? And we all know during monsoon, which is our June, July, August, pollution levels are low. Okay? So this is again at Pyramid, which is your station at the base camp of Everest. If you look closely here, forget the blue line, just the red, you see high pollution level, June, July, August. What's happening? How do you interpret that? Okay. It's very difficult for an observation person to say what's going on. Okay. Is my measurements wrong, or what's? So you can use models to try to explain. And I'm not saying this is the only explanation. This is one possible explanation, that if you look at vertical layer, because in model you can pull a 3D. So above the station, vertical up. So this is 1,000 meters above the station, which is already at 5,000. You go up to 15 kilometers, and you see high levels of pollution in the vertical axis. So even if at surface, because of clouds washing out pollutant, there's still pollution above cloud layer, where this AOD, again, is a column amount, is showing high levels of pollution. Okay? Again, a bit too technical for you, but I think what you should understand is models help you interpret observations better. In terms of policy aspects, okay, so here I'm showing you CO, okay, distribution over South Asia. And then you can do things in model like this, where, okay, what's the contribution of CO from South India, and how does it affect Himalayas? And you can see during these days, few days that I'm simulating here, there's no CO reaching Himalayas from South Asia. There's some from subsidence layer, although it's a little bit here. So you can tell that, okay, it's not really impacting the Himalayas as much during these days. Another one is sectorial. So we were doing this project on how much pollution is reaching the Arctic Circle. And then here, because you can, in model, make things zero or only simulate certain things, how much of biomass burning over California was reaching the Arctic Circle. You can do things like that in a model, which you cannot do using satellites or observations that effectively. Here's power plants in Europe that burn. These are huge power plants burning coal. What's their impact over the Arctic Circle? Okay. You can do things like that. So here, sector, whether it's biomass or power plant sector, what's their impact on a receptor location? These are things you can do using a model. Okay, so this was the station I was talking about. Here's Peak Everest. There's a station here working with the Nepal Academy of Science and Technology. So receptor location, you can say, okay, they measure high pollution here. Where is it coming from? You can segregate it in model world saying, okay, how much of it is coming from Nepal, how much is coming from India, and do a time series and say, okay, what's the contribution reaching that location? So how much of the pollution is reaching from different areas? Okay. And then in the model world, like I showed you in emission, okay, suppose, for example, sulfate. Okay, what's the contribution of sulfate from different sectors? Here, sulfate coming from industrial sources has a bigger contribution that we're measuring here. In terms of black carbon is the residential sector. In terms of organic carbon, it's coming from biomass burning. These are things you can only do using models. Okay. And then another big application these days is, okay, satellites have these data gaps. You can do some data assimilation and then fill the data. And what I'm showing you here is that assimilated data products with model do a better forecast or better prediction than model alone. Again, the application is you can combine both satellite information and model information to give a better data product. Okay, another big advantage of models, which I mentioned in my early on slide, is forecast. What's going to happen tomorrow, what's going to happen a year from now, things like that, okay? So wouldn't this be great? Wouldn't it be great if you knew this for Nagarkot before you moved, whether you could see the Himalayas or not? Okay. Because here I'm showing you CO, but we can do haze, like particulate, PM, all that. So there's advantages of having chemical weather forecast, okay, especially for tourism-related countries, for aviation. And then this is for tomorrow, actually. And this is done using a global model. Again, the scales come into effect. You cannot use this to talk about Nagarkot and compare numbers. But then it does give you some indication that, hey, there's a big regional haze. So chances are it's going to be polluted. And then where is this coming from? Again, this is also forecast. Look, it's different here. China, it's coming from fires, from agriculture burning in Punjab. So our regional haze here has a different source compared to China. Okay? So this is using a global model. Here, it's difficult to see the number here, but you can hopefully read tomorrow forecast. This is from SAFAR, India. IITM Pune brings this out for different cities. So it's going on in India, and I'm not aware of any other chemical weather forecast in the region. We are trying to do it at ICIMOD, and hopefully we'll have it up and running soon. Decision support tool. So for example, here's a what if scenario. Okay? So if you take biofuel, which is your cow dung, straw, wood, anything, biofuel, this is what the percent of people burning in terms of BC emissions. Okay? So if you take that out and make it, say, for example, electric, so 0, okay? No biofuel. What does that do to climate? Okay? I'm not talking about health, but climate. And you can see here, this is what, with biofuel, your present condition. Without biofuel, this is what it leads to. So big improvement over South Asia, but not so much in China, because China cooking is done mostly by coal. Okay? Again, here 100% emissions over Mongolia, but then it doesn't really have an impact because there's not enough BC to cause climate-related impact. Okay? This is just hot, in your language, hot off the press. This got done last week, and this is my last slide. So we're measuring air pollution in Lumbini. This will be submitted soon. So we're seeing high pollution level. Where is it coming from? We're trying to show that it's coming from biomass. And then in the model world, you can do, okay, what if all Lumbini air pollution, this is a city where Buddha was born, if we take all of the emissions from Lumbini and make it 0, saying everything electric or clean, what would that do to your CO pollution? Guess what? It's not reducing that much at all. You still get the same level pollution. Why? Because again, it's regional pollution that's coming into play. Okay? What if you measure, suppose your Lumbini emissions were too low, okay? And you increase it by 5 times, saying your emissions inventory are uncertain. Even that only increases by 150%. It should have increased, if it is 5 times more, it should have gone 500 times. So the question is, okay, it's not just emissions that drive concentration. Meteorology comes into play, and if it's a reactive species, reactions come into play. So these are things that you can, before you start going after industries in Lumbini or local sources saying, oh, you're polluting too much. Models help you decide, where pollution is coming from and how much improvement can we really get before you start chasing people out or industries out and then realize, oh, it didn't really help. Okay? So my conclusion slide, models are important to understand roles of different emissions, meteorology, chemical drivers. Most important, provide emission link between emission and observation, can be used to study past, present, and future, and they're important decision support tool. Thanks.